So welcome to another double featured lecture given by Siu-Cheong Lau and Jutan about Nakajima Quiver Varieties. So, yeah, the floor is yours.
Yeah. Thank you very much for the invitation. I'm very, very happy to be here. Today, I want to talk about the relations between Lagrangian submanifold, coherent sheaf, and quiver representation based on ADHM construction and mirror symmetry. First, I'm going to tell you the motivation and the history of ADHM construction briefly, and later I'll be more precise about the definition. This part might be a big way. So, in mathematical physics, people want to construct the anti-cell dual solution to the Yang-Mills equation over R4. But if we fix the complex structure, these are the same as over C2. According to the result of Gutenberg, the final energy solution over C2 are the same as those on S4. So, which is a one-point commodification of this. And this question was done by RTR, Junhill, Hecke, and Manet. They told us that these solutions can be constructed using some linear data, which nowadays can be understood as quiver representation. And the coherent sheaf come into this picture when Donaldson noticed that using these linear data, actually one can construct the free holomorphic vector bundles over CV2 using parallel strings. So this is Donaldson's work. He showed that there's a 1-1 correspondence between the isomorphism class of free holomorphic vector bundles and such quiver representation. Free means that we have a fixed trivialization at the infinity line inside CP2. Later I will give you the precise definition. And if we weaken the assumption on the quiver representation, actually Nakajima also showed that there's a 1-1 correspondence between free torsion-free sheaves and this quiver representation. So the questions we are interested in, or the questions we want to answer, is the following. Because free holomorphic vector bundle or free torsion-free sheaf, there are certain coherent sheaves. So we want to know what are the Lagrangians mirror to free torsion-free sheaf or free holomorphic vector bundles. And we also want to know what are the relations between Lagrangian submanifold and quiver representation. Furthermore, so we want to know what is L frame and the relation with the quiver representation. To talk about quiver representation, we also need some dimension vector, just like in the previous talk. So we also want to know what are the dimension vector means and how the stability prediction looks like. Okay. And in the future work, we also want to know the metric. But there are a lot of questions we can ask. So in this talk, we'll mainly focus on the first three. It turns out that these two are all Maurer-Cartan deformation space of some Lagrangian submanifold. And in general, we show that in this setting, the Maurer-Cartan deformation space is a Nakajima Quiver variety under some condition. This is roughly our theorism. Now I will start to be more precise about the statement and the relations.
What is the E of this?
Oh yeah, good question. This is a triple vector bundle. So we will consider Lagrangian brain. So it's a Lagrangian submanifold together with a triple vector bundle.
What is the example? What is the geometry?
So do you mean the sympathetic manifold?
What should I think of? Yeah. What now is it?
Oh, yeah. I will be more precise, but basically, is we consider the zero section of some bounding space.
Okay.
Yeah. I will introduce that. Thank you. Thank you for the questions. Okay. Now let me start to be more precise. Let's talk about the relation between coherent sheaf and quiver representation. So let's recall what is a free torsion-free sheaf. A free torsion-free sheaf over CP2 is a pair. So we have a torsion-free sheaf. So over an open dense subset, we can it will be locally free. So we can talk about rank. So we can talk about what is rank R free torsion-free sheaf. And find which is so-called framing, is a fixed trivialization of this torsion-free sheet in the infinity line inside CP2. So this is the infinity line inside CP2. And we had a fixed framing set, we had a fixed trivialization of this bundle in the infinity. Because this is brand R, so we have a brand R trivialization. Actually, the second condition implies that the first chain class vanish. We will not use it for now. So free torsion free sheet is basically this torsion free sheet and the fixed trivialization. Okay. To give you a sense that why coherent sheet are related to quiver representation, maybe let's recall Nakajima's version's ADHM construction. Okay. Let's focus on the RAM1 case. Let's consider RAM1 free torsion free sheet with second chain class equals to n. Okay. In this case, up to isomorphism, the restriction, it corresponds to its restriction to C2, which is the complement. So C2 is the complement of C2 and the infinity line. So it corresponds to a torsion free sheet of RAM1 over C2. But since the first chain class vanished and the second chain class equals to n, actually this is an ideal sheet of n points. It's an ideal sheet of n points. Because this is an affine scheme, so I will not distinguish the module and the associated coherent sheet. Okay. But because we had an ideal sheet of n points, so we can consider its quotient. We will first get a vector space Cn because it's an ideal sheet of n points. We also have module structure, so we can consider the action by Z1 and Z2. We can modify Z1 and Z2. This induces two endomorphism. Okay. So now we had a vector space and two endomorphism V1 and V2. Because the action commute, it tells us that these two matrices, these two endomorphisms also commute. Because Z1, Z2 are two variables, it commutes. So we know that this commute. Furthermore, we also had a coefficient ring inside the coordinate ring of C2 together with a natural quotient. Okay. So we know that there is also a natural map from C, and we call it I through the vector space Cn.
Can you make it large again?
Oh, yeah, right? Yeah, let me do that again. What happened? Yeah.
And also move the
How to? Oh, okay, move it away. Okay. Thank you. I don't know because. Thanks for that. Yep. Maybe let's continue because this Cn come from a finitely generated C algebra. So we know that if we multiply Z1, Z2 sufficiently many times, we should have the whole Cn. So this fact actually corresponds to another condition of the data. It's called a stability condition in this setting. It's saying that there's no proper subspace that is B1, B2 invariant that contains image of I. Okay. Yeah, I don't know. Like, is that a way to fix it?
That's the whole explanation.
Maybe there is an option where you can just fix.
Yeah, I also want to fix it.
Swap shared screen with video. So.
What happened?
Yeah, can you just make it so that the screen, this black thing is visible there only, without, because it keeps getting smaller.
Okay.
Maybe fit to window.
Yeah. To window.
No.
No, you want it bigger.
That's too small.
I think 150%.
Yeah, but this is good, but it keeps shrinking for some reason.
Okay, I'll stay here.
Okay. You will scare it. Yeah.
Thank you. Yep. So, okay. So, yeah. And there's one more thing about this linear data, that is we didn't fix the basis of this Cn. So actually, it corresponds to the isomorphism class of, it corresponds to isomorphism class of these linear data. So what Nakajima did is that actually he showed that there's a one-one correspondence between the ideal shape of the free torsion free shape RAM1 and these linear data, the isomorphism class of these linear data. Okay. There are at least three ways to generalize this result. One is that we can consider higher rank. So if we consider RAM1, RAM-R free torsion free sheaves, then the linear data will be modified in the following way. So we'll have RAM-R here, and we have one more arrow from Cn to Cr. And this time, the first condition, we have a correction term ij. There are all the relation happen at this vertex. So the RAM1 case should be understood as a special case that j equals 0. So in that case, if j equals 0, we don't have this term, so we have commuted. Yes. And actually, if one introduced the correct moduli problem, so this is a variety. This variety is the phi moduli space of the moduli problem. In the RAM1 case, this is actually Hilbert scheme of m points over C2. Using similar construction, you can also produce Hilbert scheme of m points over CR. But that's not the story of the day. So one way is consider higher rank. There are two more ways to generalize this result. And similar result will also hold for ADE surface or ALE space. Let me be more precise about what I mean by this. So by ADE surface, I mean we can consider a finite subgroup in SL2C. So this naturally S on C2. On the quotient space, we have singularity. We have Kleinian singularity at origin. And this space make a proper resolution, which is also a minimum resolution in this case. Okay, it corresponds to ADE in several ways. So, for example, the finite subgroup corresponds to the alpha ADE thinking diagram. And the exceptional current of this resolution, the incident graph also corresponds to ADE graph. So we will call the resolution to be the ADE surface. Okay. And Kraheimar also used hyperkähler quotient to construct such resolution. It gives a metric, a hyperkähler metric, which is asymptotically locally Euclidean. So sometimes I will call ADE surface, sometimes I will also call it ALE space. Okay. But what I want to say is that Kraheimar Nakajima, so is the work of Nakajima, tell us that the ADHM construction or the construction of free torsion free sheet still hold over this space. And there are at least one more way to generalize it. That is, we can consider non-commuted case. We can consider non-commuted deformations. This is due to Kapustin, Kulisov, Orlov, Baranowski, Ginsburg, and Chris. Yeah, so we can also so the ADHM construction or the construction of free torsion free sheet still holds if we consider a non-commuted space. But today we will mainly focus on higher rank vectors. So for me, this serves as an important family of examples that we can use Quiver representation to study cohesion. And of course, if you had a smooth variety and we had exceptional collections or more general Turing bundle, we know that the derived category of cohesion is equivalent to the derived category of Hasse algebra. That will also serve as an example that we can use Quiver representation to study cohesion. Okay, so this is okay. Next, maybe let's move on to the relation between Lagrangian submanifold and Quiver. Okay, to do so, I would like to introduce the work of Siu-Cheong Lau, the localized neural construction. I will skip some details. Okay, you will see. So, roughly speaking, every time when we had a Lagrangian immersion, inside a sympathetic manifold, there's a way to assign a quiver. Okay. It's actually similar to the previous talk. So for every time so for each irreducible component, because this is an immersion, we can consider its domain or consider its normalization. For each irreducible component in the normalization, we can assign a vertex. Just like the mass of index 0 does in the previous talk. Okay. And then, because we will use Arcao-Joyce model, so for each degree 1 intersection point, the intersection point will have direction, because Arcao-Joyce model is defined in the fiber product of the normalization, so it has direction. So we can assign an arrow. So it would be, so we will assign an arrow from the vertex that stands for the source Lagrangian to the target. Yeah, for example, if we have a Lagrangian submanifold that has pattern like this, later I will tell you how does this arise. And in this domain, it's just an S2, so we should assign one vertex. And there are a lot of choice of grading. One compatible choice is such that these two are degree 1. These two are two different intersection points because X can be understood as from the North Pole to the South Pole, while Y is from the South Pole to the North Pole. And according to the previous discussion, we will have two loops of this quiver. So the associated quiver is this.
Unifying is also an example, right? If you smooth a hypersmooth out, you get the configuration of Lagrangians, and then also size of that.
Smooth, yeah, even a.
Yeah.
This is a.
It will come.
Yeah. This is a local pattern of A. But because I prepared this talk for about like it's in the size of 40 minutes, so I will produce this in another way. AN will be an example. Thanks.
Degree 1 means multiplicity 1.
Oh, not really. I mean the grading in the Foucault.
Okay.
Yeah.
Okay, that's. But you don't have a U1 bundle anywhere, right? Like this.
Later
Not now.
Not now. Yeah.
GO bundle, actually.
Yes. Later we will.
complexify the deformation. So
Mhm.
generally.
Later there will be bundle. Thank you. Thank you for your question. Yeah, maybe let's try one more example. Like this one. So if we have pattern like this, just like taking the dual graph, we have two components. So we have two vertex. And there's also a choice of grading such that these have degree 1 as generated in the Foucault category. So we find that one transfer intersection point produce two reverse arrows. So actually it would be this graph. Yeah, this is actually the graph. This is the quiver, which is the double of R5 in the diagram. Okay. The reason why we care about this quiver is that the formal boundary deformation of L will actually be a path algebra of this quiver. Okay. And the relations of this path algebra will correspond to the obstruction of this deformation. Okay. In this talk, we can take the formal deformations as a black box, but if you want to know more, you can either ask the professor or you can ask me. I'm willing to explain more. Okay. But the deformation here means that we can consider the A-infinity algebra, and then we can formally deform the MK operators. So it's the deformation of MK operators. In good cases, they correspond to deformations of the unitary connection. So in good cases, it had geometric meaning. I'm happy and willing to display more if you are interested in this part. Okay. And Siu-Cheong Lau actually showed that there always exists an A-infinite function from the Foucault category of the sympathetic manifold. This Lagrangian leaps in to the DG category of this path algebra. in the case that there are no mass of index to this. And we'll call this localized mirror functor for the following reason. Because according to SYZ program, the mirror manifold will be constructed as moduli of some Lagrangians, right? Of some some hands here. So moduli of some Lagrangians. Has a point on the mirror will correspond to a Lagrangian in M. In this sense, the deformation of L would be a neighborhood of P inside M check. So in this sense, we call this localized mirror. Let me give you some examples. Let me first explain how does these patterns come up, and then give you an example how this fit into the story. Now let me explain how do we get those Lagrangians. There's a systematic way to produce those Lagrangians that is called plumbing. Let me briefly recall what that is. So if I'm given a graph D, that's a way to construct a symplectic manifold. Okay. So for example, we can imagine we have a alpha A1 graph in our mind. Then for each vertex, we can assign a Riemannian manifold. For our purpose now, we assign a Riemannian to severe. And then for each edge, we'll try to group the unit conormal bundle. But for the grouping, we'll pick some base point. We'll first pick some base point and a neighborhood of the base point, and then we group the unit conormal bundles along the base point using the following syncretomorphism.
You can also do S3, right?
Yes, we can do other dimension, and we can also have genus.
I'm sorry, in the category that you had in the previous slide, do you generally count out your 2 categories or 3 categories? Which one? Do you work with that one? With the G category?
Actually, we only use the A-infinited structure to define it. So 2-4 is 2-4. Yeah. So far is 2-4.
Okay, okay, thank you.
So far is 2-4. Yeah. Okay. Here X is the base coordinate and Y is the cotangent coordinate. So this symplectomorphism is interchange the base and the cotangent directions. Okay. And this group manifold can be completed into a Liouville manifold. Roughly speaking, it's like complete along the cotangent direction. So, yeah. The Foucault category of this plumbing space have been studied by many people, for example, Abzai Smith, Andrew Lakidi, and just quite recently after our work by Carabas and many people. But yeah, instead of computing the whole Foucault category, here we mainly consider the deformation space of some Lagrangians. The Lagrangians that we are interested in would be the zero section. Yeah, I think I have better give an example. For example, if we consider this a phi A1, the construction above will give us something like, roughly speaking, is the cotangent bundle. Because for each vertex, we assign 2 severe. And then for each edge, we pick some base point. So after grouping, it's something like this. So it's exactly the 1 definition. So roughly, the symplectic manifold is roughly the cotangent bundle of this guy.
So why are you putting that cross in? What is this cross?
Because when we do grouping, there's no this in bounded by this guy. There's no this bounded by.
I see. You're indicating that there's not this bounded by.
Yes. Yeah, thanks very much. Yeah, there's no this bounded by. So we have integrated. Yeah. So what we consider here is the deformation space of the zero section. Okay. Here come to our first.
It means the union of 2 zero sections.
Yeah, good. Thanks. The union of the zero section. So One of our results is that if you are given a graph, alpha AD or AD or no matter what graph, what diagram, so we can perform the plumbing construction using two sphere. Of course, we can do others, but here we mainly use two sphere. And then we consider the union of the zero section. Then we can perform Cheung Lau's construction. We have an associated quiver. We find that the associated quiver is the double of the graph. That is like for each edge, we assign two directions. And the formal deformation space is a pre-projected algebra. So let me recall what is pre-projected algebra. So the pre-projected algebra is a path algebra satisfied for a relation. Because for each edge, we assign two directions. So it makes sense to talk about A and A bar. These are arrow of reverse direction. And this happens at each vertex, so it is sum over tail of this arrow at B. Sum over, the sum over each vertex. Here I write down a version up to coordinate change and so on. For your interest, actually according to Karpanov and Lazaro, this path algebra is Dirac equivalent to the Dirac category of cohesion over the ADE surface. So this is actually this guy. Let me call it AL here. Is Dirac equivalent to the corresponding ADE surface.
So D was just a graph, no orientation, right? And then
No
W,
orientation.
W replace each edge with two.
Yes. D has no relation, but after plumbing and then the zero section, the associated quiver has orientation.
So you mean by the diagram is AD?
Yes. Alpha AD type. This is due to Karpanov and Lazaro.
So D can have a cycle?
Yes, alpha A1 has a cycle. Alpha core actually has. Alpha AN has cycle. Yes, maybe let's go back to simple case. For example, we can consider D to be only have one vertex and one loop. Okay. Then the plumbing construction gives us a symplectic manifold together with the following zero section is the immersive sphere that happened before, that appeared before. Okay. For convenience in this talk, maybe let's assume we have deal with conversion issues, or we restrict to the full set category that has no conversion issues. Then we no longer have series. We have a very good polynomial ring. Actually, if you compare to the previous relation, is exactly this. But yeah.
Is there an easy way to tell the L from the D?
Count the L from the D.
So if I give you a graph, you can usually just
Yes.
Each vertex is a sphere.
Yes.
Okay.
Section.
And then you get.
Yes. Yeah. And for each edge, like produce transfer intersection. Each sphere. Yeah. And then by Cheung Lau's construction, we had an infinite function from the Fukara category to the DG category of CXY motion. So this, the right hand side can be understood as a DG enhancement of cohesion with C2. Yeah. And I want to add a remark here that for this guy, for this L, the deformation space is also converted by function for different purposes.
The surface is what is a blow up at there is a -2 curve, right?
In here is smooth. There's no.
It's just C2.
Yeah, this is actually
This is
fiber of.
A1, right?
This is the immersed sphere in C2. This is regarded as a Lagrangian.
Yeah, this is a Lagrangian.
No, I mean for the mirror, for the
The
not for
mirror.
the, not for the mirror, for this Kapranov's story that it's.
This is not A1. This is not A1. This is a phi A0.
I see.
Yeah, you can draw up like
Yeah, alpha A1 is this one. So C2 more gamma. Resolution will be the T star P1. Yeah. Will be the T star P1. The mirror side. And this is alpha A. Yeah, thanks. Okay. Now we can start to answer with such explicit functor in hand. We can start to answer what are free torsion-free sheaves. Because in our previous example, we see that the free torsion-free over CP2 corresponds to a torsion-free sheet over C2 that has a canonical extension to CP2. So we can now start to answer what are this. Okay. We find that the free Lagrangian should be the union of the zero section and the cotangent fiber. So where F3 is the cotangent fiber of S of the V squared hex. Yeah. To get the intuition why this should be the right answer, maybe let's go back to the previous example. So we had underlying graph to be just one vertex and one loop. Then the union of the zero section and the cotangent fiber. In this case, we only have one vertex, so we only have one cotangent fiber. In a three-dimensional space, the intersection pattern is roughly look like this. So the intersection pattern is roughly look like this. So let me call this to be FP and this is L. Okay. To get the intuition why this should be the right answer, maybe let's go back to some good cases. Okay. Yeah. Because of time, but actually this pattern will appear in the Lagrangian torus vibration of C2. In that case, L would be a Lagrangian fiber, would be a fiber of the Lagrangian torus vibration. And in that case, FV would be a section. Now I can start to tell you the intuition why this should be the right answer. So okay, so now we had a functor to C2, and then we want to know what are the Lagrangian mirror to free torsion-free sheet. So maybe let's consider the simple case. So the RAM1 free torsion-free sheet, the ideal sheet. So if we had an ideal sheet of one point in C2, we know that it fit into the following choice sequence. This is a RAM1 free torsion-free sheet with section number 1. In the derived category of coherent sheet, we know that it fit into the following distinguished triangle. But according to homological mirror symmetry, we know that the derived category of coherent sheet is equivalent to derived Foucault category as a triangulated category. Hence, it should preserve the triangulated structure. On the other hand, by XYZ program, we know that the trivial line bundle should correspond to a trivial section, which is our FV here. And in good cases, the zero section, just like actually they are okay in the vibration of in the Lagrangian vibration of C2, the L would be the fiber. So the skyscraper shape should correspond to the fiber. Hence, one should expect that certain union of them. One should expect that certain union of them will mirror to our free torsion motion. And the aside is that if we come back to the pattern, this is my E, this is my F. Then think about what is the associated quiver. You may notice that this time we have two vertex, okay, because we have two components. We still have those two degree one intersection points, so we still have these two here. But this time we have two more. So we have these two here. So we get back the quiver that we used before to construct free torsion free sheet. Actually, we did the following calculations. This time, we'll equip the Lagrangian submanifold with flat vector bundles. Okay. So we will equip the normalization of this L frame with flat vector bundles. So over each kinetic component, it could have different ranks because this is a flat vector bundles in the normalization. Intuitively, we regard it as how many copies of the multiplicity of this component, just like in the previous talk, we consider D1 cover or D2 cover of the curve, so of the Lagrangians. So here, the rank of the vector bundles play a similar role here. So we regard the rank as how many copies they have. We compute the Maurer-Cartan deformation space. We find that it's the following quotient stack. So you may notice that the obstruction is exactly the equation that appeared before. And the isomorphism class of this deformation, okay, it's just the quotient stack correspond to the previous variety, previous Nakajima Quiver variety. And then there's also an interesting fact. Because of this fact, we know that an element in the deformation space will correspond to a representation. This element is stable in the sense of representation if and only if there's a vanishing of some Lagrangian Fourier cohomology. So this is an element of representation. It's stable if and only if we have a vanishing of some Lagrangian Fourier cohomology. Here L is the zero section, L frame is the free Lagrangian, which is the union of the zero section and the cotangent fiber. Furthermore, we find that, okay, we rigorously show that this element, okay, as an object in the Foucault category, is mapped to, we call that this is functor to the DG category of CXY module. So first, we'll get a complex of sheaves over C2. And we show that in this case, the cohomology of that complex is exactly the torsion free shear over C2. And if we homogenize it, this complex tells us how to do the extension. We get the free torsion free shear over C2. So in short, in summary, is that these Lagrangian submanifold are mapped to free torsion free shear. And the deformation space coincides with the moduli space of free torsion free shear. Yep. More generally, we also did the following calculation. We also calculate the formal deformation space of LV in general, L frame in general. The setting is as before. So we had a graph, we do plumbing, and then we had zero section and the cotangent fiber. In this case, the associated quiver would be the free double quiver of D. The setting is similar to Nakajima. So Nakajima define quiver variety start with a graph, and then we do the double and then frame. So here we get the same thing. And we compute the formal deformation space again. Instead, to be a pre-projected algebra, we had a free pre-projected algebra, which is AQ3. So the relation is similar to before, but we had a correction term. So we had a correction term, just like an analog of before. Yes, I almost finished. Okay, so and the corollary of this guy is that the deformation space, we can also equip the Lagrangian submanifold with bundles, with refractory bundles in the normalization. Then the Maurer-Cartan deformation space would be a Nakajima Quiver if we fix a stability condition. If we don't fix a stability condition, we will have Cauchy stack as before. Right? If we do so, we will have the Nakajima Quiver. Yeah. So yeah, I might be a bit rushed here. So yeah, and furthermore, previously I only tell you that I only tell you the construction of plate torsion friction over CP2 case. Actually, similar result also holds for the AD surface. So it's just a generalization of CP2. It will also hold for AD surface. And so actually this is a starting point of a lot of things, because Nakajima Quiver variety is interesting because it has rich geometric representation theory. For example, is Borel homology can be realized as a representation of a deformed cosmology algebra. And the key ingredient in that construction is the kernel is the Hecke correspondence, which is the kernel of a Fourier-Mukai type transform. And in an ongoing project with Siu-Cheong, we find that these ingredients actually can be realized as a support of some Lagrangian homology. So roughly speaking, the idea is the following. Because we know that the deformation space of the free Lagrangians are Nakajima variety. So if we consider the Lagrangian Fourier complex, we will first had a complex over the product space. So it's like a family of vector space as B1 as the deformation parameter vary in the space. So we had a complex over the product space, and its cohomology would be a sheaf over this guy. The cohomology would be a sheaf over the product of Nakajima Quiver varieties. And we are able to show that if we consider H0, the degree 0 Lagrangian Fourier cohomology, the support, it will be a sheaf, and its support would be the Hecke correspondence, which is the kernel of the Fourier-Mukai transform to define the rising operator or and so on. Okay. So I guess this will be the end of my talk. I'm willing to display more details.
So for the relation, do you need to do holomorphic curve chart to get the relation to get the Jiawei Quiver?
Or we really count the constant in this setting because they are exact. The zero section in the counter construction, they are exact. They don't bound.
Draw a picture.
Oh yeah, sure. So, for example, I don't know whether this works. At least one should work. Let's see. So, for example, in this case, because these two are exact, it doesn't bound any of this. We mainly count the constant that map to these forms. We use Moore's model, so actually we count that. Yeah. Let me see. We mainly count the constant that's mapped here and then flow to the minimal point of the sphere. We'll finally flow to the minimal point of each component and so on. But there are others. There are other constants.
Can you deform your count to get some not
Or in some cases, we have some actual, yeah. Of course, yeah. In the AN case, we can deform it and then get some deform the Lagrangian. If I understand correctly.
No, not really. I can ask later. So one other question. Why do you get the pre-projected algebra instead of the multiplicative pre-projected?
Oh yeah. That's a good question. This is because we didn't compute the whole Foucault category. We only consider a neighborhood of this Lagrangian. So the deformation space is like as an open ball in the multiplicative. Yeah. So we only have a pre-projected. Yeah.
I mean, it's not a question, but just just a suggestion. So
yeah, no problem.
The first paper that I wrote, I considered the self-plumbing the same.
Oh yeah, I should cite.
You saw this? No, not citing.
Yeah,
so there I consider so you take an equator and you do a Dane twist around that equator. So that Dane twist acts on this deformation space.
Oh.
And I computed what that does.
Oh, okay.
So you might want to
take a look at this.
Take a look at this paper and maybe generalize.
You consider then twist action on the Maurer-Cartan space.
Yes.
Oh, okay.
Deformation space. And it's a non-trivial action.
Yeah. What kinds of Riemannian manifold you assign for the vertex? Like because
just a self-plumbing of a sphere. So
two sphere.
Just one sphere.
Oh, one sphere. Yeah.
One sphere.
I see. Thank you.
I mean, I can send the paper to you.
Yeah.
Okay.
Yeah, no problem. I can find.
Are there more questions? If not, then let's start this.